In this video, I'm going to go through the examples from our Nearpod lesson, January 26th. They are on work, energy, and power. This is review for the semester exam. Okay, in the first example, we've got a roller coaster cart here, and you can see it must be somewhere throughout the ride. It already has kinetic energy by the time it reaches A. And you can see here that it tells us we have 160 kilojoules. Remember, that means 1,000 joules. And if we already know how much kinetic energy it has, the first part says let's calculate the speed. So there's our equation for kinetic energy. EK equals 1/2 mv squared. And we're just going to need to move that around to solve for v. Since I have a 1/2, if I multiply both sides by 2, I'll get rid of the 1/2. And since mass is attached by multiplication to velocity, or speed in this case, I will divide both sides by m and get rid of the root sign, or the square with the root sign. So let's put in our values. And when I pick up my calculator, punch those all in, I get 23.1 meters per second. And I'm just going to put that value up here at the side so I can erase this and continue working. Now the next part tells me as it moves from A to B, this isn't a perfect situation. I am going to lose some energy to overcome friction. So it just manages to roll over the crest. So let's say it has no kinetic energy when it gets to the top. So we need to use the conservation of energy here, and we're going to create our own formula. So I'm going to start with my kinetic energy, and I'm just going to write an A because that's the value there, equals the work done to overcome friction plus whatever potential energy it has up there at B. Okay, so let's put in some values we know. And we are given the fact that this is 40 kilojoules. And the equation for potential energy, mgh. So if I rearrange this around, if I bring the 40 over to the other side, I'm going to get 120 times 10 to the 3. And then underneath it, I'm going to have the mass, 600, and g, 9.81. If I pick up my calculator and put all my values in, I get 20.4. Make sure you stop and you check that you can get these values as well. And I'll clear this off so I can do some more solutions. Next part. At C, we have some water that's going to slow us down. Make 3 suggestions for what happens with this kinetic energy. Well, that energy could go into heat, which is usually what happens when we have friction. It could then dissipate into the water or into the air. I could also have some noise, so sound would be the energy. And I could also have some damage done to the car. Hopefully not if this is on purpose. But I could also have that go into internal energy in the actual cart itself and then dissipate into the environment as well. Okay, so a train has a total mass of 7.5 times 10, and that should be to the power of 5. I was missing the ability to put a superscript. Now it accelerates from rest at a rate of, oh wait, this is all about acceleration. So the very first thing I'm going to do is I'm going to write down suvat, because I know I'm going to need to put my information in here. Okay, so it's from rest, so that means u equals 0. It reaches a speed of 24, that's my final speed here, velocity, in 60 seconds, obviously is time, and it says calculate this train's acceleration, so I'm going to put a question mark there. So I'm going to go to my formula sheet and look for the equation that has A, V, U, and T. So you can see I've got it here, and we're going to make my math easier because this value is 0, so we know that's going to cancel out. So 24 over 60. I pick up my calculator, and I have 0.4 meters per second squared. Now, we need the resultant force. Remember, the resultant force is also called the net force, the unbalanced force, the resultant force, the overall force. They all really mean the same. And that equation, F net equals ma. So again, let's put in our value, 7.5 times 10 to the power of 5 times my acceleration. I pick up my calculator, and I get 3.0 times 10 to the power 5 newtons. And I'm going to put my values over to the side again so I can give myself some space. All right, so the train now travels with a constant speed of 24 meters per second. As soon as you hear constant speed, we want you to think Newton's first law. All the forces must be balanced. Okay, so that is a very key term for you to be looking for in these questions. Now, it also says the opposing force is 7.2 times 10 to the power 4. And since it's traveling at that constant speed, we also know that the force of the engine, I'm just going to ENG, must be exactly the same but in the opposite direction. I'm going to put my frictional force as being the -1. We're going to need that for the next part of the question on my next screen. Okay, so I have the values there at the top from the other screen. By considering the work done by the train's engine in 1 second, calculate its output power. Okay, so power is going to be work divided by time. And my work would be what I'm doing to overcome the force of friction times its distance over time. Now notice it's traveling at a constant speed here. So my distance over time is telling me it's going 24 meters per 1 second. So if I put these values in, 7.2 times 10 to the 4, and my distance over time will be 24 meters per second. Pick up my calculator, and I get 1.7 times 10 to the power 6 watts. Remember, power is measured in watts. Don't get that confused with the W standing for work, because that's the symbol for the measurement, where this is the symbol for the unit of power. Now, once the train begins to travel up the slope, they're going to have to increase to maintain that speed. So one of the things you need to realize is as I'm going up the slope, I'm going to have an increase in potential energy, and that's going to need to come from somewhere. Remember our equation, power, work over time. Work is also the change in energy over time. So as I go up the slope, that means this value here, my energy, is going to be more than if I was just going along a flat surface. Well, I hope that's helped you with these two examples from class using work, energy, and power.